So, we finished up talking about irreversibilities. These basically kind of enforce these concepts within the second law to be true. We cannot get a system and its surroundings back to their initial state because of these irreversibilities. Friction is kind of a common culprit. The idea that you take good mechanical energy and convert that into heat energy, or convert it into sound, that's now energy that's out in the environment that you can't get back. So anyway, just something to think about there. Those are irreversibilities. Now, the Carnot Cycle was one of the first. I shouldn't say it's the first. It's one of the first. I don't know if it's the first, but it's one of the first proposed reversible cycles. Okay? Carnot proposed this reversible heat engine that could be operated, and we drew some conclusions that if this thing was in fact reversible, that means that this is the ideal situation. It's not something we're going to be able to construct. We could construct things that kind of look like it, but not exactly. But the fact that it's reversible, what it does is it sets the performance limits. Right? Efficiency and coefficient of performance. It sets the limit as to how successful or how efficient a device can be, because all irreversible, right? So all irreversible cycles are less efficient. And the temperature of the reservoirs, the source and the sink, control the efficiency. Or performance. So the only thing determining the efficiency of a reversible device, and the reversible device being the most efficient, the only thing determining that efficiency is the temperature of the reservoirs with which it's exchanging heat. Right? So, what does that mean? Well, let's draw a device that operates in a cycle and exchanges heat and produces a net amount of work. What would that be? That's what we call a heat engine. A heat engine is a device that absorbs heat from a high temp source, in this case, or body. Let's call it a body. Some high temperature body. So this could be a fire, this could be a nuclear reaction, this could be a coal fire. It's going to provide heat at a high temperature, and we're going to pour that heat into a boiler unit. This is a heat exchanger where I'm taking hot air that's coming off of this fire or hot water coming off of a nuclear reaction, and I'm running it through a heat exchanger where there's a cold stream inside, and that cold stream is a high pressure, low temperature liquid, most likely water, that's going to boil off in the boiler, and then we're going to run the output of that boiler into a turbine. That turbine's going to generate work out, as turbines do. Through the turbine, it's going to expand, and it's going to push these aluminum fan blades, or however the turbine's constructed. It's going to generate rotating shaft energy that's going to go out as work out. That's my mechanical energy that I'm extracting from the engine. I can use this to power a generator, turn a locomotive or a car in tires or whatever I want to hook this up to, flour mill, etc. Okay. Now on the bottom is another heat exchanger we call the condenser, right, or a radiator or something like that. Some place where we can reject heat to a low temperature body, which we often would call a sink. Something that's absorbing heat we would call a sink. Right? This could be a lake, a river, it could be the atmosphere, just somewhere I need to dump heat, because I can't, remember, I believe it's our friend Claus's tells us that you cannot produce net work. I can't get work out perpetually by exchanging heat simply from this high temperature body. I've also got to do something else. I can't turn all this heat into work. I've got to get rid of what I couldn't turn into work. So this in, these two out. And then I could possibly repeat my cycle from there, but normally what happens is I've got low pressure coming out of the turbine, and I need high pressure going into the turbine. It's normally how most of these are constructed. Now, I can't get the pressure to increase in the boiler, at least not easily. I'm going to have to put in some pretty complicated mechanisms to make that work. But what I could do is I could inject a high pressure liquid into the boiler. If I inject high pressure liquid into the boiler, then I can get high pressure vapor coming out. To do that, what I can do is if I get the fluid all the way down to the liquid phase in the condenser, then I can operate a pump. Pumps are really good at increasing pressure of a liquid. I do have to put just a little bit of work in to do that. And this is normally the easiest way to get high pressure. Again, I've got to have high pressure here. Well, nothing here is going to increase the pressure. In fact, it's probably going to drop. We'll worry about that in the fluid mechanics class later. Let's not worry about the pressure drop right now. Let's assume, for our purposes, I've got constant pressure in the boiler and constant pressure in the condenser. So nothing in here increasing the pressure. I've got to increase the pressure here by putting just a little bit of work or power input into a pump, increases the pressure. Now I've got a high pressure output, cycle repeats. Okay, so again, if we look at first law for the entire engine, it's a closed system. It's a closed cyclic system, meaning that work in minus the work out plus the heat in we'll call QH minus the heat out we'll call QL. And because it's a cycle, that's equal to 0. You don't want this thing blowing up. And if it's non-zero, it's either going to blow up, it's going to exhaust if it's negative. If it's positive, it's going to blow up. Or if it's negative, it's going to exhaust. Or it's possible it just reaches an equilibrium point where it reaches a 0 point. Okay? And any of those could happen. So what happens? Well, I've got net work out. The difference between work out and work in. So I move this over, subtract that. So that difference ends up being QH minus QL. The efficiency, what we call the thermal efficiency for this engine, is what we want, the net work out, divided by what I have to do to get it. Well, I have to put heat in, or QH, to get it. And if I substitute this in here, this simplifies down into 1 minus QL over QH. Okay. Now, I'll prove to you in just a little bit that this is true if I've got a reversible. And when we introduce the second law, we'll come back and I'll show you that this is true. If we have a reversible device like a Carnot cycle or any other reversible cycle, then the ratio of heat transfers is equal to the ratio of temperatures. And again, if we accept the second law as true, that's really easy to prove. And we can do that when we start chapter 7 in just a second. Okay? All right, let's talk quickly about refrigerators and heat pumps. We talk about a refrigerator. An air conditioning unit is a refrigerator. That's a device that is, if I draw my compressor, My compressor is a device that's going to add energy, work, or power to my fluid stream. So I'm going to have mass coming in, and I'm going to have mass going out. And the whole goal of a compressor in a refrigeration unit is I'm going to have vapor coming in, and I'm going to increase the pressure and the temperature of that vapor by squeezing it and adding energy to it. And I get it so hot that it will actually now lose heat to the high temperature body. All right, so I've got some high temperature reservoir up here that when I run the fluid through what we call the condenser coils, heat exchanger, excuse me, that's, if you look at a central heat and air system, that's the big thing that sits outside of your house or your apartment that the fan spins in and it pulls and blows hot air out. That hot air you're feeling is this QH. That's the heat coming out of the house. So it's the heat plus the electricity coming out of the house. From the condenser, we run into what we call an expansion valve. Now, if we had a lot of time, or if we were setting you up for a Thermodynamics 2 course, or in a Thermodynamics 2 course, we'd really talk about supersonic flow, compressible flow, and what happens through a throttling process. For us, we're just going to say, if I take a high pressure, because it's coming out of the compressor high pressure, if I take a high pressure fluid and I allow it to expand, when that expansion occurs, it's going to go to a lower pressure and a lower temperature. So through this process of the expansion valve, what's going to happen, and again, think about an aerosol can that you hold open too long. You go from high pressure inside and allow it to expand to a low pressure outside, it gets cold. It gets so cold that when I run that refrigerant then through an evaporator, another heat exchanger, it's going to be so cold that it'll actually absorb heat from a low temperature body. And that's the whole goal of the refrigeration unit, is to remove heat from the low temperature body. The air inside your house, the food inside your refrigerator, whatever the purpose of that device, whatever it's trying to cool. And then the cycle is ready to repeat, right? So again, if we look at the first law for the whole thing, I've got the work in plus QL minus QH, add the in, subtract the outs. If it's a cycle, that's equal to 0, meaning the first law simplifies to the work in is equal to QH minus QL. Basically, the net work in is equal to the net heat out. Now, if we talk about the coefficient of performance, Steve, why isn't it an efficiency? Well, we don't call it an efficiency because it typically exceeds 1. We only call efficiencies values that are less than 1. Coefficient of performance, the COP, for a refrigerator will typically exceed 1. In fact, we kind of want it to, unless it's in a specialized situation. Now, it still represents what we want. What we want is QL. Our goal for a refrigerator is to cool the low temperature body. And to do that, we've got to put work into it. Most of the time, this is the larger quantity. So therefore, typically this ratio is greater than 1. Now, just like with efficiency, this needs to be a unitless quantity. I need BTUs over BTUs, joules over joules, watts over watts, horsepower over horsepower. Whatever units of energy or power you want to use, just make sure it's the same top and bottom. And as we've discussed before, if I plug this in there, this simplifies down to 1 over QH over QL minus 1. And again, the maximum value, the maximum performance for this refrigerator would be for a reversible refrigerator, Carnot refrigerator, or any other reversible cycle. And I can substitute in the ratio of temperatures, TH over TL for QH over QL here, and that holds true. And I gotta stop there. Hopefully I'm gonna beat the clock. All right, we'll pick up there on the next one.